Question. Okay, part A should feel pretty straightforward. You're just going through ratio tests, finding your potential interval of convergence, and then testing your endpoints. Any questions with part A? Part B, substitute f of x with the function I gave you and see if you can clean that up and convince yourself what the limit is going to be. All right, any questions with part B? After we replace f of x with the function they gave us, the 1/3 cancels out. And if we divide by x, the first term is the only term that will remain as a constant. All the other terms will have x's remaining. So limit as x approaches 0 will zero all those values out except for that first term, 2/3 squared or 2/9.
Does it work?
It does, yep. We do get 0/0. You can do L'Hopital's rule. Yeah. Good. L'Hopital's rule can work too. But if you're doing L'Hopital's rule, make sure that you're showing that 0/0 indeterminate form before you jump into applying it. Got to show that there's a hole before you can go through your steps. Okay, try part C.
So you don't really need to like have like 0 because it can be plus. Sorry, the general term 0.
We don't have to worry about plus C. Why is that? Yeah, because they're not bounced. The C's will always wash out if they're not bounced. Plus C will only show up if it's asking for the indefinite fill. Any questions with part C? Try part D. Or which part? We can't do what?
It doesn't start at 0.
You can start at 0 or 1. You don't have to specify which number you start at. You just have to create a definition that works for either 0 or 1. Yes. Yeah, because you want to start at, because you're starting at 1. Yeah, we do that.
How would I specify I'm starting at 1 for like
You don't have to. Yeah, they're okay with not indicating that summation notation. So you can have different variations of your general term, and as long as it works, either typically students start at 0 or 1, they'll give credit there. Yeah. Okay, for part D, what kind of a series is this? Geometric, right? So we have a formula for that, right? We have a sum formula for that.
hard to be honest. Yes.
Yeah, that's, I think it's, yeah, I mean, you're always going to get some bleed in from AB topics. it's not all just going to be BC, BC, BC. There's going to be some parts that quickly in. So. Okay, before we, first of all, any questions? So tomorrow's tests, 2 FRQs, it'll just be front and back. One side will be a particle motion FRQ. The other side will be a Taylor series FRQ. For the particle motion, it's calculator. It's meant to be calculator, so that means you don't have to show your work. Just have to, if they ask you for acceleration vector, just use your calculator, find that value. You don't have to show any work for that. But just make sure you go through the FRQs that we've done for particle motion. Know your speed formula, know your distance formula. So yeah, review that. You only have to show work if the problem specifies it, right? If it specifies, show work that justifies your answer, but typically your particle motion is inside your calculator section. And then, go through the rest of your packet for the practice more of I think we've done most, if not all, of the Taylor series FRQs. So hopefully you guys feel pretty comfortable there. And then there was a worksheet that I gave out yesterday that I did for morning review today. So hopefully that will give you some additional practice for tomorrow. Okay, so you will get to use your calculator, but on the Taylor series FRQs, I want to see your steps. Okay, I want to see your steps, but you can use your calculator to justify whatever you want to check. All right, any questions? Right, so let's go into our packet 2A, and we're going to go through the odds from pages 9 through 16, and then whatever we don't finish, I'm going to be checking for homework on Monday. So I'll be checking all the problems, page 9 through 16 on Monday, but we can start working through that, and I can kind of walk us through and review some of these concepts with us. Okay, page 9. We're going all the way back to related rates here. So as a reminder, with related rates, we always start off with some equation that we're building off of. Maybe that equation is Pythagorean theorem. Maybe it's volume of a cone. Maybe it's volume of a sphere. But after we start off with some algebraic or geometric equation, we build the derivative. And when we build the derivative, every variable gets impacted by time. So v will become dv dt, s becomes dx dt, x becomes dx dt, right? So every variable gets impacted. Okay, so start off with 1. We're just going to work through the odds so that we can kind of see a variety of problems, but your homework will be all the problems, even and odd. Start off with the very first related rates problems that we did, which was a right triangle problem involving a ladder. Okay. When you're deciding the sign of your rate, is it positive or negative rate? Don't depend on direction. I think sometimes we feel, oh, down is negative and left is negative and right is positive. It depends on what's happening to that value. If that value is getting smaller, you want that rate to be negative. If that value is growing over time, you want that rate to be positive. So you do need to kind of picture the problem in motion. Not every downward motion is meaning that you have a negative rate. Sometimes if you go down, it may lengthen that value. If it lengthens that value, you want that rate to be positive. In this case, left is positive and down is negative, right? Because as well, the way that I drew my ladder situation, as it's moving away, we know dxdt should be growing. So we don't want to say, oh, it's going left, so therefore it's negative. It's what's happening to that base length. That base length is growing, you want that rate to be positive.
Try to show you find the rate as well.
Yep, I agree. So we saw with Pythagorean theorem, x squared plus y squared equals z squared. You don't have to use those variables. That's what I used. And then every variable gets impacted by time. So find the derivative of each variable first, and then attach a d over dt for that variable. So x squared becomes 2x dx dt, y squared becomes 2y dy dt, and z squared becomes 2z dc dt. Number 3 is a cone problem. So with cone problems, we know we have to set up similar triangle relationship because we want to find that connection between radius and height so that we can replace our volume equation in terms of either R or H. That way we can find the derivative without all these variables getting in the way. So, and for number 3, we realize that we're looking for dHdt. So that gives me a hint that, prefer to get our radius to be replaced in terms of H. If we can get our volume equation in terms of height, then H has an easier time producing dHdt. Okay, next page, page 10. Reviewing some of the theorems here. So extreme value theorem is for number 1. Number 2, you see mean value theorem. Number 3, you see Rolle's theorem. So as a reminder, extreme value theorem is we're trying to find absolute max, absolute min. So find your critical points by setting your derivative equal to 0. Make sure every critical point that you find is inside the interval, because if it's a critical point outside the interval, that's not part of our problem. So you take your critical point, you take your endpoints, plug them back into the original function, and then compare the y values. Highest y value is your absolute max, lowest is your absolute min. And as a reminder, mean value theorem is going to be the even problem, but just with mean value theorem, you're trying to guarantee a slope. So you find the slope between the two endpoints, you set it equal to the derivative, and that will help you locate the point where that slope on the curve is going to match the slope between the two endpoints. And then with Rolle's theorem, it's the same formula. It's just that your f of a and f of b happens to be the same y value. So that's going to force the slope 0. So Rolle's theorem is slope 0. But the reason why that's occurring is because your f of a is equal to f of b. If that's the case, that's always going to 0 out. And then you're just basically finding a critical point for Rolle's theorem. Once you can confirm that it's a smooth curve, continuous, and differentiable and continuous, and the endpoints are the same, this is going to 0 out. Your slope is going to be 0. So you just simply set f prime equal to 0 and solve for it. You're just looking for slope 0 somewhere along the graph. But mean value theorem, it can be slope 0, but it could also be other slopes as well, depending on what the endpoints are giving you. After we get done with page 10, let's skip to page 13 so we can kind of just see more variety of problems, because page 11 and 12 are just related rates, more related rates, mean value theorem and Rolle's theorem, and extreme value theorem. And then page 13 is first derivative test for concavity, derivative graphs, particle motion. So finish page 10, number 3, which is Rolle's theorem, and then go to page 13 after that. So number 3, we're just confirming that the graph has the same y value at the endpoints, which is going to force a slope 0 between the 2 endpoints, and therefore we can guarantee a slope 0. Then we can set the derivative equal to 0 and solve for x. And when you solve for x, make sure that your x value solution is living between the endpoints. And then a nitpicky thing here is for mean value theorem and Rolle's theorem, if you land at the endpoint, that's not good enough. It's got to be between. So endpoint is outside the interval. It needs to be between the endpoints. Okay, page 13. Trying to find a relative minimum. So go through first derivative test, find f prime, set f prime equal to 0, find your critical points, populate your slope sign line, test each subinterval, and then positive value would be positive slope, negative would be negative slope. And if you can figure out your behavior of your slope sign line, then you can look at the arrows to decide where your relative min or relative max will be. Page 13.
AP topics, right?
I'm sorry.
These are AP.
These are our AP topics, right? Yeah. So we should be able to get through this packet by midweek next week, and then I have another packet, just BC topics. Okay. Number 3 is an application of second derivative test. Remember, second derivative test is not the same thing as test for concavity. Second derivative test does the same job as first derivative test, but is using the second derivative to confirm whether the graph is a relative max or relative min. So with second derivative tests, we're pairing the knowledge of slope and concavity. If I know the slope is 0 and the graph is concave up, I should be able to convince myself I'm looking at a relative minimum, right? If my graph has a slope 0 and concave down, then I should be able to convince myself that point must be part of a relative maximum. So number 3 says f prime of 5 is equal to 0. So at that point, the slope behavior is 0. F double prime of 5 equals -3. We know also at that point, the concavity behavior is negative, which is concave down. So if the slope is 0 and the graph is curved downwards, we must be looking at a relative maximum. Page 14, number 5, particle motion. Speed is increasing whenever velocity and acceleration have the same signs. So create your velocity sign line, create your acceleration sign line, line up your two number lines, and then look to see where is the behavior, velocity and acceleration being the same signs. Okay, let's keep working for another 5 minutes. Does anybody still need page 14? Sorry, page 13 rather. Just to let you know, page 16, I pulled those problems from calculator active parts of the multiple choice practice tests. So just know that page 16 is meant to be using your calculator to look for critical points or using your calculator to assist you in finding your solutions. Okay, so again, your homework, page 9 through 16, I'll check that on Monday. But tonight, see if you can focus your attention on looking over packet 1 and looking through all the Taylor series FRQs. If you can look at the problem and know what the first step is, then that's a good sign. That means just keep looking through a problem until you see something that you feel like you want to rework or that you're not exactly what your first step is, then take the time to work through it. But hopefully you guys feel comfortable heading into tomorrow's assessment. Okay. All right, can we get your phones? Thank you. Great. Great, thank you.
I don't think so. I think there was a behind of you. You don't have to. Is there? Yeah, there is.
Yeah.
On group.